Good morning everybody. Uh, Myself Sarup Bag from Department of Mechanical Engineering. So, today I will be discussing on this special topic, that is the numerical modeling of additive manufacturing processes. So, basically the numerical modeling means, in this case we will try to discuss more on the finite element modeling of the additive manufacturing processes. So, you know that you have already coverage of the additive manufacturing process, but still I want to discuss the very basic, the overall view of additive manufacturing process. So, it is a layer by layer deposition process and it creates 3-dimensional object, and it is a kind of additive method in the sense that it eliminates the all conventional manufacturing processes and opposed to that of subtracting manufacturing process. So, definitely it is a kind of effective utilization of the materials is possible in additive manufacturing process, but some sort of computer interface is required in additive manufacturing process, and because if you want to develop a certain product, that CAD model of this particular geometric shape of the product is required, then we follow some kind of the slicing technique. That means we decides what can be the layer size and layer thickness, and that everything we computerized. This we store the data in the different file format, and when there is a need we execute this data and instruct the actual 3D printing machine, or I can say that additive manufacturing machines, to deposit layer by layer a particular material. It can be metallic material, it can be polymeric material. But finally, once the object has been developed, then we try to follow some sort of the finishing operation. It can be any kind of very precision finishing or kind of the other kind of the machining operation we can perform to find out, to achieve the desired surface roughness or surface finish if this particular component. So, this is the overall view that additive manufacturing works on. Now, point is that if we look into this figure, is that possible to achieve this by layer deposition process, exactly that what way we can looking for kind of the oval shape object. Now, if you divide into small layer, and then even if it is very small layer, then some sort of the roughness will always be there after deposition at the on the surface. So, achievement of this roughness, or to minimize the surface roughness in layer by layer deposition process, we have to optimize that what can be the layer thickness. So, accordingly, but some sort we cannot avoid to follow some sort of the finishing operation to achieve exactly this dimensional tolerance of this particular product. So, that is why, that is I can say the other side, it means that the kind of drawback or maybe issues associated with the additive manufacturing process. Anyway, try to look into this thing, that layer by layer deposition process fashion, and we take it this the geometrical shape from some digital model, and normally we use some CAD model developed before that things, and then we accordingly we can deposit the layer by layer in this additive manufacturing process. But of course, why it is so important? Because there are lots of design flexibility, and as compared to the other conventional manufacturing process, or other way we can say that it can replace so many conventional manufacturing processes, and then all product can be possible to develop following the only single process, that is the additive manufacturing process. Now, relaxation on the assembly, that means it maybe we can say that it can reduce the assembly work. So, if you want to make a very complex shape, maybe it's conventional process use the separate parts of these components and then one by one assemble and then get the actual product, but that relaxation in that some sort of the assembly process can be reduced in this additive manufacturing process. Even reduce the lead times, because we have to synchronize all these different manufacturing process or different different components that finally assemble to make in a single component. So, in that sense it can reduce the very lead time and wastage of material, because additive manufacturing is the layer by layer deposition process. So, it completely eliminate the subtractive manufacturing process. So, in that sense the wastage of material can be minimized in this case. So, these are the typical benefits we normally get from the additive manufacturing process. But if we look into the development of this process, there are very three basic parts. Here I have mentioned here, one is the motion control, that means what way we can move deposit the material, or maybe for a stationary material, what way we can scan the laser to get solidified and deposited according to the size of the component. So, this is one part, that is the motion control. The structure properties depends on the how fast we are moving or how slow we are moving the laser or scanning it over the substrate material, or what way we are depositing the material. So, this is the motion control is one component. Other thing is the what kind of the heat source, it can be laser, it can be electron beam, or some sort of kind of arc, that simply arc welding machines we can utilize as a heat source in this particular process. And finally, the other part is the most important part is the what kind of the feedstock material we are using. Either we are using in the form of a raw material in the form of a liquid, or in the form of a solid stock, or in the other form of the material we can utilize, or maybe in the form of a wire, in the form of a powder, or in the form of a sheet we are utilizing. Based on that, different additive manufacturing technologies has been developed. But anyway, our focus is to understand the different aspects of the or maybe modeling approach for the additive manufacturing process. Now, if we look into overview, overall three different kind of the sources we can utilize for the development of the additive manufacturing. One is the laser, mostly widely used this thing in this process. Second is that electron beam can be used, and other options we can simply use the source, then arc, which is available simple welding machines. So, therefore, that arc can also be utilized as a heat source for the development of the different additive manufacturing technology. So, if we focus on the beam, here in the laser beam, the different processes has been developed. We see that laser beam, that can be wire based, that means the raw material we can utilize in the form of a wire, or powder, the raw material in the form of a powder. So, but in that both the cases we can utilize as a laser as a source. Now, wire can be wire laser additive manufacturing in the form, that means simply feeding the wire from the outside and then synchronize with the laser source. Laser source simply hitting the wire and the depositing in a very controlled way on the substrate material to develop this technology. This is the one way. Other way is that powder can be put in the stationary bed, and then you can move the laser source and to melt the required position following some scanning path or according to the design or strategy. And other can be the blown of the powder, that means powder you are projecting the powder and utilizing the laser source, and then at the same time and melting the powder and creating the almost near net shape product. So, this is the source of the laser, and this is the form of in general this is the form of a raw materials we can utilize for the development of the additive manufacturing technology. Other way, the similar kind of the process can be utilized, but source can be different. So, in this cases electron beam, and you know that electron beam, any technology based on the electron beam, that can be under the vacuum chamber. So, in that cases also raw materials in the form of a wire can be utilized, in the form of a powder can also be utilized. So, based on that different technology has been developed. But if you compare laser and electron beam, I can say the electron beam is more costlier, and even you have to maintain all this thing, everything in the under vacuum chamber. So, in that sense, so electron beam technology is the most costlier, but other way as compared to the laser, but other way it is advantageous that the manufacture component we can keep it, that it is a protected environment such that the contamination or kind of oxide formation from the outside atmosphere can be eliminated completely using the electron beam technology. Even it is a costly technology, but till if you want to achieve very good that means almost defect free component, and this thing or highly precision component, or we are handling the very high costly material, then electron beam technology can be much more suitable as compared to the laser beam. Other side, suppose there is a need to enhance the deposition or maybe large deposition rate. So, in that case wire arc additive manufacturing technology is more suitable, but in that cases you cannot expect that much of surface finish as compared to the laser or electron beam based technology, because arc based technology is there when there is a need of the high amount of the metal deposition, and definitely the surface finish is not that much needed. In that cases probably we can go for the arc based technology. We will discuss one by one maybe this different additive manufacturing technology development. Now, laser is most widely used in additive manufacturing process. So, there are two different ways it can be utilized. One is the bed based, powder bed based, other is the powder feed based. So, I am talking about the powder because now powder based polymeric material is the well established additive manufacturing technology. So, broadly you can classify into two types: powder bed, what it works, you can see that there is a laser source is there, or maybe electron beam source is there, and there is a table. So, we can fill the bed with the powder, and then the laser will be scanned according to the path defined, then it melts only that selective position, melting and solidification happen in that particular selective position. Then we can go for the next layer. So, simply moving the z axis, the one upward the according z axis movement according to the thickness of the layer you are supposed to deposit. And then this can be done over a chamber that is filled with the argon or nitrogen, that is a kind of inert gas. So, this will protect this component from the outside atmosphere, and this way we can develop the powder bed based technology. But powder feed based technology, you can see that here, that the same time laser and powder is basically projecting on the substrate material, and that while projecting the powder on a particular position, laser beam heat source is also focusing, and at the simultaneously it is melting the substrate material, and as well as the melting as well as depositing this thing. So, here it is not exactly happening over a closed chamber kind of this thing in the powder bed based technology. It is a kind of open atmosphere, but definitely along with the powder and this thing laser beam source, we normally use as kind of shielding gas. What way we can utilize any kind of the welding process. So, any arc welding process also, there also we can use the shielding gas just to protect the molten pool from the outside atmosphere. So, similar strategy also we can follow here in the powder feed based technology. But what are the difference in application point of view? Because powder feed based technology here there is no such restriction to the size of the component. So, it is open. So, in which direction we can move, we can maybe develop the component layer by layer deposition, that is possible in case of the powder feed based technology, but the size of the component is limited in case of the powder bed based technology, because it depends on the what is the size of the chamber. Same thing also happen if you understand the electron beam process also, because the product component size is limited by the size of the chamber. So, these two different technology has been developed depending upon their application or need, but mostly powder feed based technologies when there is a need to some kind of the repairing work. So, there is a need to repairing work only in a particular position, there is a need to deposition of the material, then definitely powder feed based technology is most suitable there. From that purpose powder feed based technology has been developed. Here in details that powder bed based technology. So, already you have discussed powder based technology. It starts with the 3D CAD model and then decides the path, and then we can build strategy, everything has been pre-decided, and then once we can follow the layer by layer deposition just by XY table, we can utilize the movement of the XY direction, and maybe once the one plane that particular layer thickness is done, then we move the Z axis. So, Z axis, then we work looking into the strategy, everything decided predefined. So, that strategy we can follow for the next layer. In that way successive layer normally developed in this particular in the powder based technology, and already mentioned this thing that chamber is filled with some kind of the shielding gas chamber. So, therefore, we can utilize or we can develop this thing, the product which this shielding gas actually protect from the contamination by the atmosphere. Similarly, if we powder bed based technology, although we are talking powder based technology, but if we look into this, not only powder based technology, any additive manufacturing technology, it is associated to lots of parameters need to synchronize at the same time, or other way we can say the optimization of the so many parameters in additive manufacturing process is very difficult, and getting this optimized set of parameters is a huge task in additive manufacturing process. And of course, that optimized parameter may be that existence of this optimum parameter, the narrow domain. So, not a wide domain, one parameter can vary. So, that is normally does not happen in case of the additive manufacturing process. So, that is why this is one kind of the tedious task to decide the what kind of sets of the parameters, but before that we need to understand what are the parameters associated, say as an example in case of the powder bed based technology. First thing is the just simply pick up the heat source. If you see what are the, say suppose laser source, laser we are utilizing. So, what is the laser power, what could be the beam size, what should be the pulse condition, what can be the pulse parameters, pulse duration, what can be the pulse frequency, all the parameters associated with the heat source. Apart from this thing, then build strategy. Build strategy means what with the scan path, how you can decide the scan pattern. So, scan patterns means, for example, continuously moving one direction, or we can move some zigzag way, or how to handle this if there is a curvature is there. So, how can the motion control during the curvature when depositing over a curvature. So, that kind of scan pattern and scan strategy is basically is required in these cases. Even for the not only this thing, the scan speed also, how fast we can move from one point to another point. It depends on the, mostly depends on the what are the heat input power unit length during this particular process. So, it depends what is the laser power utilizing this thing, accordingly you can decide that what can be the velocity, how fast we can move, we can develop this product. At the same time, we have to look into the solidification time. So, before depositing for the next layer, so we have to allow the previous layer to solidify. So, that kind of strategy has to be developed in case of this thing, and according to that we need to consider all the parameters. Apart from this thing, the feed material. So, that suppose feed material, what are the form of the feed material. So, if you utilize the wire, so what can be the wire size suitable for this particular heat source, or if you consider the powder. So, powder is associated lots of parameters. The powder, what can be the powder shape, is the almost spherical shape, and what can be the shape and what can be the size, what is the powder size, it normally the is vary over a range. And then distribution, whether what distribution, different size of the powders, their distribution, because that also improves the product quality, surface finish also. And then apart from this thing, feed material, what can be the layer thickness. So, in a powder bed based technology, what should be the thickness of the layer. And then definitely material properties. So, it means that other way I can say the powder properties, which is different from the is a bulk material. So, for example, if you make a powder from a bulk material, the properties of the bulk material and properties of the powder are different. So, we have to consider the properties of this powder. So, in the development of this additive manufacturing processes. Now, there is also process specific, the powder bed temperature and built environment, what kind of the shielding gas are utilizing this, what can be the powder bed temperature. It means that maybe depositing one layer. So, some sort of the preheating normally happens before depositing for the next layer. So, all kind of parameters needs to optimize to get is the well set the process, or I can say the additive manufacturing technology. Even it is also true in case of the powder feed based technology that we have already discussed. The powder feed based technology with just depositing the material from the heat source, and at the same time we are focusing the material. So, melting the position and depositing the material on the substrate. So, this also associated with the lots of parameter, and that what way that in this cases the maybe which cases the laser is focusing at that point, this area of the projected area of the powder particles can be minimum, so that it can utilize effective utilization of the laser source is possible in case of the powder feed based technology. So, anyway, that we have already seen, and then most of the process, maybe we can say the direct energy deposition having the, this is one kind of the additive manufacturing technology. So, it is lots of utilization nowadays. So, in this case powder based technology can be used, or direct energy deposition we can use the wire based technology, maybe directly we can utilize the wire, we can feed the wire externally and then heat the wire. So, that is there. So, coaxial feed of powder or wire can be utilized in the form of source can be laser or source can be the electron beam. Now, but it is necessary the powder deposition has to be synchronized with the heat source, and we do not use the any kind of the powder bed system in case of the directed energy deposition technique. Setting up the DED is more easy and maybe cost effective to produce the larger parts, and when there is no limitation of the size of the components in this case. But DED can also be used for coat existing structure. So, maybe existing structure we want to perform the coating on this existing structure, that can also be done even if you want to do some kind of repairing work, then in that cases DED technology can also be utilized. Now, DED technology is more aligned to development of the wire arc additive manufacturing process, just normally handles the metallic material. So, that is why the development is normally happening in this particular area, in this particular direction. Now, if we look into the direct energy deposition techniques, based on this the concept, the wire arc additive manufacturing process has been developed. So, wire arc additive manufacturing process means simply we can utilize the same principle of the material deposition which normally occurs in case of the welding process. So, same welding machines can also be utilized this thing. Thus, normally development is happening, maybe plasma arc welding process we can utilize for the development of the wire arc additive manufacturing process, but in that cases there is a need to feed the external material in the form of a wire, and then that can be this plasma source can be utilized to melt the wire and the depositing the material on the structure. So, this is the one, but apart from this thing gas metal arc welding and can also be utilized this, because in these cases the metal transfer is the integral part of the system, the welding system itself. So, it is a continuously feeding the material and the material is depositing over the substrate, and then it is a, if we control the motion or develop the strategy, then layer by layer deposition is possible using the simply the following the gas metal arc welding, the metal transfer of the gas metal arc welding process. So, there are several ways to this thing, the different types of the metal transfer, the globular kind of the short circuiting, spray, even if you use the pulse heat source, then pulse spray transfer of the metal transfer is associated with the gas metal arc welding process. But difficulty of the gas metal arc welding process is the controlling of the metal transfer is not that much of smooth, because in principle the gas metal arc welding process there is a continuous feeding of the material, and in that cases it is the additive manufacturing technology is the more rely on the what kind of the metal transfer is basically happening in this case. So, in that sense maybe short circuiting metal transfer can be the more controlled as compared to the other type of the metal transfer, but till we can utilize the gas metal arc welding process for the development of the wire arc additive manufacturing technology. But if we think about little advanced level, then that is called the cold metal transfer. We can say it is a kind of advanced level of the gas metal arc welding process. So, in this case the cold metal transfer, the metal transfer is actually more controlled as compared to the GM method. So, in that sense it is different. Definitely in CMT process the metal transfer is normally happening in the short circuit mode, and some kind of the mechanical detachment technique we normally utilize in the CMT process. So, it is not like that as a gradual or normal procedure what way the metal transfer happens in the gas metal arc welding process, but in CMT when the droplet creates and droplet is in contact with the substrate material, then we can put some kind of the backward forces to the system, so that the metal will be detached from the substrate material, and this way we can control the metal transfer by using some external mechanical means. So, this frequency can be much more this droplet transfer, and it is a more controlled way the metal transfer is possible. So, that is why CMT process is more useful for the development of the additive manufacturing technology. Now, if we look into that numerical model of the additive manufacturing process, now I come to this what is the actual topic on these things. Before that I have just tried to give you some kind of the overview of the additive manufacturing process. Now, why there is a need for the numerical modeling of the additive manufacturing process? Since already mentioned that this additive manufacturing process is basically associated with the lots of parameters. So, finding optimize each and changing each and every parameter, and maybe finding the then performing the experiments to establish the particular process is really time consuming, involve lots of costs, also involvement lots of material, all this thing involvement is there. So, in the other sense we can say that if we can develop some model in additive manufacturing process, then we can try to understand the differential influence of the process parameter by utilizing the heat transfer model. Probably it can reduce the number of experiments for the development of a particular process, but definitely some sort of the experiments are needed to validate the developed model. So, for that purpose there is a need to understand for the development of the numerical model, or maybe I can say the mathematical model of the additive manufacturing process. Now, if we look into the physical process involved in the additive manufacturing, it is actually very complex, and it involves, we can summarize this in this way, that if you look into how it works. So, first thing is the material deposition. So, material deposition is there, the additive manufacturing process. So, we can say it is associated with the heat and mass transfer, because utilizing some sort of the heat source, then it is heating the substrate material, and then substrate material deposited on a particular substrate material. So, therefore, it is associated with the heat and mass transfer from the mathematical point of view. Then apart from this thing, definitely when utilizing the heat source, it is melting the material. So, when is the melting and depositing the material. So, definitely it should be associated with the some solidification, melting and solidification, and sometimes if the laser intensity is very high, it can create some vaporization of the material, can be possible in case of alloy system when you try to depositing the alloy. Apart from these things, surface tension dominated free surface flow, it means that when depositing the particular material, that it forms certain kind of the bead shape depending upon the material surface tension or the what are the temperature at the which temperature are depositing the material. For example, if the material is very superheated material, then probably the surface tension becomes less in that cases, then you can expect that much of not bead size can be different, but if in certain material deposition happens just above the melting point temperature, probably in that cases the surface tension can be different as compared to the very superheated material. In that case you can expect the bead shape can be different. So that is why to understand the bead shape also we need to look into the what are the surface tension dominated free surface flow. That is very important in additive manufacturing to predict the free surface profile or bead profile in this particular process. Then what are the different type of the heat source you are utilizing. So heat source means not only the heat source, the interaction of the heat source with the material is very important. For example, you are utilizing the laser, but the interacting the laser with the bulk material is the solid metal, and interacting of the laser in the powder, the two different aspect. So absorptivity of the laser or maybe depth of penetration of the laser when it is interacting with the two different same material but the two different form, then laser material interaction can be different. So in these cases the interaction can be very complex as well. So therefore we normally look into that thing, the interaction can be represented in a form of a heat source model. So that is very important in these things. Apart from this thing, free surface modeling, just we have already explained this free surface modeling, the over the bead profile, what that is also important in this thing in additive manufacturing process. So now all this aspect, the physical aspect, looking into all these physical aspects and developing of a single model is really very difficult task, and in terms of the computational time and computational cost as well also. So therefore most of the cases what we can do, we look into the individual component and then we analyze the same or maybe we can try to develop the different model in the different scale. For example, if we do the heat transfer analysis, we will be able to know only the temperature distribution. If we do the flow analysis, then we will be able to know that what is the flow of the molten metal after the deposition. So in that cases we will be given output as a flow field. If we do perform the free surface modeling, we will be able to know what can be the profile of the bead profile in a particular process. If we do the stress analysis, then we will be able to know what are the stress field, residual stress generation in a structure. So that is why we can do the individual, but if you want to know the what can be the microstructure or if you analyze the solidification behavior, then we need to reduce the length scale and time scale. So in that cases there is a need to the multi-scale modeling approach is required for the development of the additive manufacturing technology. Now we will try to utilize maybe one by one, maybe first we will start with the heat transfer model, then we will try to look into the how it can be developed the flow model, and then look into the what are the different aspects of the free surface model, and finally we try to look into the what we can develop the heat transfer model. I am not going into that the multi-scale modeling approach, that is the different aspect, and maybe we need to understand the several aspects for the development of this particular model. So here we try to look into the very basics part. Say in additive manufacturing, definitely it is associated with the solidification process, but solidification of the alloy is very important. What is happening in the Moschi zone? Moschi zone means in the which zone the between the solidus and liquidus temperature where the liquid phase and the solid phase coexist, and in that case the concentration gradient temperature is very important, or maybe transport phenomena, that how it is evolving. The transport means the what way the elements is transporting within this very small structure, and in that if you understand this phenomena, definitely this solidification of the alloy, already mentioned this thing, we need to go for the lower length scale and time scale. Maybe the grain scale modeling approach is required in this part to understand the solidification behavior. So which is different from the continuum scale, where in the which scale we normally analyze the heat transfer, material flow behavior, even for the stress analysis. So that is why there is a need to the multi-scale approach if you want to understand the solidification of an alloy associated with the additive manufacturing process. Now the interface, it creates definitely interface of the different phases, and maybe different microstructure constitute. In that cases also coupled with the physical field such as the temperature and concentration. So, if you want to interface, other we can say the interface or microstructure model also, definitely the scale will be lower, the different scale, but we can take the input from the temperature distribution and what are the concentration distribution that actually help to develop this is the lower scale model in this particular case. So, if you want to track the interface maybe different phases or even for the free surface also, then we can use this phase field model, this thing immersed boundary level set method, front tracking, all these particular techniques we can utilize to understand the lower scale, the different interfaces between the different structure, microstructure part. And even these methods apply to small domain, maybe the continuum scale from about 0.1 micrometer to 10 millimeter in this particular zone. I mean to say that suppose if you want to look into the microstructure, so microstructure is not possible to look into the microstructure for the whole domain in the continuum scale, which in a I can say that in the millimeter scale you are looking into the temperature distribution. So, that domain, but whole domain it is very difficult to develop the microstructure model. Microstructure model we can focus on the very small domain, maybe in the micrometer scale, that domain, and from there we can develop the model and we can analyze, we can see the microstructure for this particular domain. So, that is why it is a microstructure at different scale, we can look into that. Now, we come back to starting with the thermal analysis. So, thermal analysis can be performed which is independent of the mechanical analysis or other kind of the analysis. So, we can do simple thermal analysis by solving the heat conduction equation, and then if needed then we can loosely couple this thermal analysis to develop the stress analysis model. For example, we can utilize the data for the, if we perform the thermal analysis, then we will be able to know the temperature distribution and at different time as a function of time. Then we can utilize this data for the analysis of the residual stress, but it is a weakly coupled. First we perform the thermal analysis, it is completely done, then utilize this data, this for the stress analysis. But in these cases we are not utilizing the data for the stress analysis, takes as the input for the thermal analysis, that kind of things we are not doing. So, it is a loosely we can do this thing, or maybe we can say the weakly coupled analysis can be done. But one point is that when you look the thermal analysis, it is very important to look into the material properties to give the correct result from the thermal analysis. So, that is why temperature dependent material properties is very important and in the particular analysis. Now, once we look into the, say you are talking about the mathematical model, or maybe we can say the numerical model of the additive manufacturing process, but the mathematical tool or techniques can be different. One is that we can either utilize the finite element, we can utilize the finite difference, even we can utilize the finite volume method. But additive component is associated even for the residual stress and distortion, that is we have already, it is already mentioned these things. Apart from these things, maybe if you look into the wire arc additive manufacturing process also, here we can compare it with the multipass welding process, and what are the modeling approach we can follow for multiple welding process. The same kind of strategy can be utilized in case of the additive manufacturing process development. But in general, and we normally utilize the finite element method, and sometimes fully coupled or maybe weakly coupled, or maybe we can say the sequentially coupled thermomechanical analysis is normally done. That will give you the some idea the residual stress generation, because residual stress and distortion is one of the most important aspect associated with the additive manufacturing process. So, sometimes we try to work into that, how we can manage the residual stress in a additive manufacturing component. Now, apart from these things, when you try to look into the heat transfer, definitely mention that the how we can represent the interaction between the heat source and the substrate material, that can be represented in the form of a heat source, and that most of the cases we can utilize the volumetric heat source we can define, and that volumetric heat source, that heat input can be utilized through the governing equation. So, it can be input, I will show that how it can be done. And apart from these things, in general when you look into the additive manufacturing process, the model development, so element activation and deactivation technique is very important in these cases, because it is a kind of progressive model, the progressively you are adding the material to the domain. So, keep on adding the material to domain, so that can be better way in finite element approach. We keep on activating the element when along with the deposition of the material, and then this activation technique has to be known, or this technique should be understand to develop the additive manufacturing process. Now, apart from this thing, that we have to, I am just trying to represent the what are the physical aspect has to be looked in the for the development of the model. Now the path can be linear or path can be curved, that means when you depositing the material it can be linear path, it can be some curve is there. So we have to look into this thing in the solidification behavior or how to handle and the moving heat source and how to take care of the element activation technique when there is a curved path, that means the heat source is moving or material is depositing over a curved path. So these are the important aspect, but if you look into what are the different elements means what are the different modeling components will be there in associated to the additive manufacturing process or in this particular complex for the development of this complex numerical model. So one is that first thing is that prediction of the temperature distribution. It is a most simply by solving the heat conduction equation you can predict the what are the temperature distribution in the domain, because it is helpful to make the strategy temperature distribution just to know not only the temperature distribution, predict the shape and size of the different heat affected zone or molten zone, not only that, because temperature distribution can be utilized for the prediction of the some sort of this microstructure or maybe solidification behavior is possible to predict from the temperature distribution as well. Apart from this thing, from the temperature distribution able to predict the shape and size of the molten zone and the heat affected zone. Even from the temperature distribution we can to some extent we can predict the what can be the solidification time. So how much time it is taking to solidify, because in that cases we have to look into the cooling phase. Then definitely the mass addition to this thing, so or maybe other way I can say the mass addition to the domain, we have to, this is another component, or I can say that simple way the energy addition to the particular solution domain, because it is a kind of deposition process. Then if you want to more actively or more precisely predict the temperature distribution, or if you want to understand what can be the effect of the surface active elements, then material flow behavior is important. So it is basically enhance the calculation accuracy associated with the heat transfer in additive manufacturing process. Now final structure anyway, so heat transfer analysis, material flow analysis, the free surface flow, free surface profile. Apart from this thing, finally after solidification what can be the stress level and distortion level in a structure, that can be done simply performing the thermomechanical analysis, that is or that normally predict the residual stress and distortion. So these are the typical component of a complete additive manufacturing process. So we have to look into all these components individually to understand the modeling approaches in the additive manufacturing process. So first look into the heat transfer analysis. So if we look in transient thermal analysis, basically predict the temperature as a function of temperature, we have to use the transient heat conduction equation. So this heat conduction equation or energy balance equation is given here, rho Cp dt by d small t. So here small t is the time component. So our temperature is varying with respect to time, and density specific it is there, and the Q is the heat flux. So it is simply Fourier heat conduction model. We can extend it into 3-dimensional way, or that we solve this heat conduction equation along with the boundary condition, we will be able to predict the temperature distribution. But if you follow the finite element method, then you have to discretize the domain, you have to create the elements to the whole domain, and probably in that cases when you creating the whole domain you are assuming this can be the final shape and size of the domain. So then when you are depositing in the first layer, and then gradually you can keep on activating the element. So after deposition first layer and second layer, so that element activation techniques has to be modeled before that. So that according to the path, it is a predefined path. So then over this domain, when the domain is basically increasing, when layer deposition, domain size actually increases. So every time we need to follow the solve the heat conduction equation, and that but heat conduction equation has to be solved over a span of the time step. So it is a very small time test. I can give an example, maybe the 1 to 10 to the power minus 3. So 0.001 second gap, for example, this is, suppose this is the time step. So even within that time step, every time you need to solve the heat conduction equation to get the temperature distribution as a function of time. So this is the typical procedure for the development of the heat transfer model. Now if you look into this, in this particular equation, the internal heat generation term Q dot, this is associated with the governing equation. Now when you develop the that heat source model, so heat source model, if you assume this is a volumetric heat source model, so then volumetric heat source model, then that heat source model has to be incorporated this term in the governing equation. So but definitely it is defined heat generation per unit volume, per unit time. So then the whatever heat source model has been you try to utilize or suitable for this particular process, that actually implemented or maybe incorporated through this internal heat generation term in this governing equation. So, that is the part of the heat transfer analysis. Now, not only the governing equation, we have to look into the boundary interaction or boundary condition in this case. So, what I can define the boundary in general, if you look into this, the substrate material is there over the deposition of the, if you consider this as a whole as a solution domain, and what are the activity on the boundary. So, over the boundary there will be the heat loss to the surrounding by the convection and radiation. So, this is the one thing, and other thing is the, if you see this is a control volume. So, the heat source is applied, that basically heat is interacting, the laser source is interacting over the boundary. So, that can be implemented in the form of a boundary interaction, but if you develop the volumetric heat source model, then that heat source model is incorporated to the governing equation only. In that cases you can neglect the surface flux which is interacting through the boundary by the laser or maybe creation of the arc, that may not consider in this particular case. So, rather what way we develop the heat transfer model, just to we consider the volumetric heat source, and that volumetric heat source is basically incorporated through the heat conduction equation. Just we explain this thing. Now, mathematically how we can represent the boundary condition, here you can see that it is a kind of the this see I assuming that it is a Q dot internal heat generation term, it is a volumetric heat source term. So, that passes through the or maybe incorporated through the governing equation, but over the boundary this is the heat loss by convection, this is heat loss by radiation. So, what will be the heat loss by convection and radiation? That is with the heat conducted to the domain of the boundary. So, whatever heat conducted to the domain, basically at this point what is the heat flux through the mode of conduction, that is equivalent to the heat loss by the radiation and convection. So, in that way we mathematically represents the boundary interaction. Now, there is a two domain in general. So, maybe this domain is responsible for the heat loss and this domain may be responsible for the heat input, but in this case if you are not considering the surface flux as a heat input, rather we are considering the volumetric flux. So, therefore, we do not need to consider the surface flux from the heat source. In additive manufacturing process, if you see the heat source model, first is the heat source model. In the additive manufacturing simulation, the heat source model is the Goldach's double ellipsoidal heat source model, and it is a more realistic heat flow distribution, and when there is a in the filler material is required. So, if you additive manufacturing process actually over the substrate material, the heat source is there, but at the same time material deposition is also there. So, therefore, in that cases we can utilize that hybrid heat source model, but shape can be, we can follow the double ellipsoidal Goldach's double ellipsoidal heat source model, but we can account the this shape, we can that volume can be accounted, which is because of the material deposition on the substrate material. So, that we can be accounted, and in that cases both can be represented is a volumetric heat source, and then we can follow the model of the Goldach's double ellipsoidal heat source model. So, here the different power distribution for the filler and the base material, you can distinguish different power distribution for the filler and the base material. Base material means you can follow the Gaussian distribution, and for the filler material you can use the uniform distribution. That can also be done for the development of the heat source model. Therefore, part of the total power is delivered to the base material by the Goldach's model. That means, if you suppose this is the substrate material and this pool is developing the, so this part is the over the substrate material, you can consider as a Goldach's double ellipsoid. Some part of the energy is here is the transfer to the domain in the form of a Goldach's double ellipsoidal heat source model, that can be accounted this thing. But some of the material deposition is also there. So, this material deposition, the intensity can be uniform, and accordingly you can make the energy balance from the material deposition, and you can some part of the energy can be accounted for this material deposition. So, this is one heat source model part 1, and this is another heat source model, it can be different also for the part 2. So, both are responsible for the energy transfer to the solution domain. So, this way we can represent the heat source model for the two different components. So, this is the one way, one approach to account basically the material deposition for the development of the heat source model. In principle, internal heat generation, already we have mentioned that internal heat generation is applied to the filler material Fe elements whose inside the is a control volume, that we already discussed this thing, because this heat generation this is the volumetric heat source. So, this can be incorporated through the internal heat generation term in the governing equation. but we can develop the model, estimate the model with the is maybe a heat source model, but it will be associated with the different parameters and the distribution, and it accounts the what are the laser power utilizing, the efficiency term also has to be accounted, and based on that we can develop the heat source model. Now, other thing is the numerical modeling of the additive manufacturing. The other part is the specific element activation techniques is normally utilized to simulate the material deposition process. So, in this cases the two different approaches exist. One is the inactive element method and is the quiet element method, but here we can look into the quiet element method. So, these elements are already present, this thing. Let us look into this this way. So, suppose this is the size of the substrate material. Now, material deposition is happening about this thing. So, material deposition happening, this is for example, this is one element. So, over this heat source is moving this particular direction. So, next another material deposition, another element. So, keep on activating this element and that enhance the basically it increasing the solution domain. So, this is the one way, that is the once the heat source moves, keep on activating the element. This is the simple way to model these things, but before developing this model you can develop the geometry, you can utilize this geometry and you can discretize the geometry also, but this element becomes inactive. So, when the one layer is deposition is over, so all elements becomes active, then you go for keep on activating gradually these elements depending upon the scan speed, or we can utilize this maybe the temperature distribution also. So, based on the temperature value we can say that which part is basically the deciding. So, this is the temperature range over which when the temperature exceeds certain value we are activating this element, and this when activating this element this becomes part of the solution domain, and that this way we can keep on activating the element and we can develop the this model. Here you can see that material properties are progressively switched from the quiet to the active values according to the deposition process. So, these are the elements from the quiet to the active state, heat can be decided by the temperature and the material properties value can be assigned this way. If you look into this temperature dependent material properties, where these are the specific material properties, phi or gamma material properties, and other part the material property, and gamma is the activation function. So, this gamma is the activation function. So, that activation function decides, that is also is a function of temperature. So, depending upon the actual temperature value we can activate that activated element, or we can decide the material properties, what should be the material properties of this activating element. So, this way we can develop the model. Now, if we specifically look into the wire arc additive manufacturing process, so in that cases also that amount of the total heat energy in this case, that sum of the energy delivered by the arc and the due to the transport of the metal droplet. So, that we have already discussed that this when the wire arc additive manufacturing process, definitely it is associated with the metal deposition process also. So, we have to look into the total energy can be counted, that one part from the heat source, it can be laser, it can be arc, and another part can be considered for the because deposited material, because deposited material is a superheated material. So, this droplet transfer to the domain. So, when droplet transfer to the domain, definitely it is having some kind of the thermal energy. So, that both energy has to be counted when you try to develop this model. I can say it is a one kind of that important aspect associated with the modeling approach. But sometimes we enhance the modeling approach already if you count the convective heat transfer in the molten pool can also exist. In that cases we need to go for the convective heat transfer model. So, simply the fluid flow model. So, in that cases need to solve the Navier-Stokes equation, but it is computationally expensive. So, most of the cases we normally neglect that convective heat transfer model, the fluid flow model, but if we possible to incorporate the material flow model, then the enhance of the accuracy of the model can be enhanced. So, that is why heat transfer model is sometimes necessary to consider, and sometimes we can eliminate maybe effect of the convective heat transfer. Convective heat transfer is the material flow inside the molten pool. So, we can neglect this part molten pool, but we by developing the complete the fluid flow model, rather in other way we can compensate the material flow behavior in conduction heat transfer model also. There what we can do in that cases, we can artificially enhance the heat transfer coefficient. So, effective value of the thermal conductivity sometimes we can consider just to suppress the, or maybe other way to account the material flow in a material flow behavior in any kind of the molten pool. So, there this enhance the conductivity, and this putting the high value of the conductivity and K effective values, and this K effective we can utilize in case of the simple heat conduction based model. So, there we can get the temperature distribution. That is the other way to suppress or maybe to consider the effect of the material flow in a conduction based heat transfer model. Now, we are talking about this the conductive heat transfer model. Now, here we can take an simple example that how it works, what we can develop the model also. Say take the solution domain, I have taken one cross section. So, it may be more associated with the welding process, but other way we can say it is also applicable in case of the additive manufacturing process. So, if we see EFGS is the say solution domain, and maybe the domain can be, if it is a symmetric, then we can create the symmetric surface over this boundary condition symmetric surface, we can consider the 0 flux. This is the heat transfer model, this thus the gradient should be 0. So, suppose this is the y direction, so in that cases del T by del y should be 0 in this case. Now, this is the domain and there is heat is interacting this. So, normally heat is interacting, that is the Gaussian heat source we can utilize. So, it is interacting. So, this Gaussian heat source, either this heat source can be represented in the form of a this heat flux, or this heat source can be represented in the form of a the governing equation Q dot. In that cases you need to develop the volumetric heat source. So, heat source, or you can say the volumetric flux. So, when you are incorporating the volumetric flux Q dot, so in that cases the heat source model is required. Or suppose depending on the process you want to apply only the surface flux, then you can incorporate the surface flux using this term, the boundary condition term. So, this is the governing equation, it is a heat conduction equation, a tangent equation also, and this the governing equation has to be solved, and then what are the boundary interactions. So, over the boundary will be the heat law, not the bottom surface, because bottom surface maybe it is in contact with the some substrate material. So, maybe you can use some contact condition also here in the bottom surface, but other part in the convection and radiation heat loss will be accounted. So, this is the convection heat loss and this is the radiation heat loss, and this is the surface, all are the surface activity. So, that is the boundary condition, means definitely the over the boundary surface what are the different activity will be there, and it is the Kn, the heat conduction, heat is conducted, what is the value heat is conducted on the surface at this point, K it is defined over the surface only. So, that making a balance in the heat transfer. So, this can be act as a boundary condition, and over the domain, the whole domain, solving this equation they will be getting the temperature distribution. It is a 3-dimensional form, they can the temperature distribution, but in finite element model, suppose this is the node, the finite element model, this is the elements and nodes, the discretized domain. So, you will be getting the temperature at each node point value. So, then finally you can make it as a distribution of the temperature over the domain. So, this is the output, but here you can see this is the governing equation applying the domain over the domain. If it is a symmetric surface, you can create the, you can reduce the, define the symmetric surface, then you can reduce the computational time, number of elements, number of nodes in numerical methods. But if it is a not symmetric surface, does not exist in a particular problem, then you have to consider the whole domain. And here also this is another part, the H. So, here if you see the convection and radiation, but finite element discretization can be different if the, because here temperature variable and the fourth power. So, in that cases we can take the combined effect of the convection and radiation, the simple equation H equal to in this particular way, and then you can make it equivalent to the equation of the effective heat transfer coefficient that accounts both the actual heat transfer, convective heat transfer from the surface convection as well as the radiation effect, both can be combined there and find out the effective heat transfer such that final H will be the here effective heat transfer and T minus some reference temperature. So, this way we can modify this particular boundary equation, and definitely if there is a symmetric surface, you have to normally the symmetric surface, the any variable, the gradient should be 0. So, here it is y direction, so therefore it will be 0 in this particular surface. Now, whether we need to apply the surface heat flux or volumetric heat flux, it depends on the problem, but remember, so in additive manufacturing process normally we can utilize the volumetric flux is more important. So, when you try to incorporate the volumetric heat flux, then we have to define some volumetric heat source model. I think this is all about the conduction heat transfer model. That is all for today, and more we will be discussing maybe later on. So, thank you very much for your kind attention.